Okay, 6.2 is on a special type of data set called a normal distribution or normal curves. In order to be a normal distribution, a normal curve, basically what you have to have, again, we call them normal because actually they occur a lot in nature. Almost every standardized testing will land in a normal curve. And any type of measurement typically lands in a normal curve. Like when we're measuring weights of kids, heights of kids, weights of newborns, and things like that. What it is, it's how the data values are spread. All right? And so what they have to, in order to be a normal curve, what you have to have is when you draw out the set, the shape should be bell-shaped. All right? It should have a bell shape to it. And so the graph of a bell shape is given down below. The biggest thing about it is it has to have the following rule. We just talked about mean, median, and mode in the last set of notes. And for it to be a normal curve, the mean has to be the same as the median and the same as the mode. Alright, again, special for these normal distributions. Mean is equal to median is equal to mode. Most of the data, and we'll look at what we mean by this, but most of the points, the scores, the heights, or whatever we're talking about, will be fairly close to that mean, median, and mode. Right? Because again, mode would be the most, where most of the points actually land. What's other thing that's really nice about it is that the data is symmetrical, meaning you have the same amount of values above the mean as you do the below the mean, and they land at the same points. Alright, so when we go look at the curve, this is what we mean by it's the bell-shaped here. The peak, this peak value, whatever that peak value is, it is the mean, median, and mode. Alright, whatever that is, and I'm going to write it out as the mu, because mu is the mode, or median. Mean. It is the median as well because they're equal. Alright, and so again, that peak represents the average, the mean. That peak is also the median. It's the middle value. Half of the data is above it, 50% is above, 50% is below, and it's also the mode, right? The peak means that's the highest value, meaning that point occurs the most often, whatever that value is. That value occurs the most. So it's the mean, median, and mode. And so what we mean by symmetrical means, if I take this curve and I could fold it over that middle value, the left side and the right side would be exactly the same. All the points on the left side would land at the same moment. So if I pick a point here, there's a point on the other side that's the exact same value, and it's the same distance from the mean. So if this was distance, we'll say it's negative since it's on the left side, it would be the same as the positive value on the right side. Again, they'd land on top of each other. Whatever this area here would be exactly the same as this area here. So if this area is 2, this area over here would also be 2. Right? And so again, if this was the negative 5, this would be positive 5. And so that's what we mean by it's symmetrical. 50% of the values land on this side, 50% of the values land on that side. Again, that's what median means, right? Half of the data set lands above the median, half of the data set lands below the median. In this case, it also happens to land at the same place as the average, and the mode in this case. Again, it's what makes normal curves special. And they're called normal because they occur in nature normally. Alright, it's a very common distribution is to be a normal curve. Alright, we're going to talk about standard deviation. That has to go with our normal curve. We're actually going to look at a special rule in a second. So reminding you what standard deviation is, we found it in the last set for finite cases. Remember what standard deviation is. It tells us, on average, how far the data values are spread from our mean, from our middle value. Alright, in this case, in the normal curve, how far they're spread from our peak of the bell-shaped curve. The bigger the standard deviation, the fatter the bell shape, because again, they're spread out further from that average. The smaller the standard deviation, the thinner the bell shape, because again, they're spread out close, right? Thinner means they would be tightly packed around it. And so just to kind of give you an example, if we have a big standard deviation, it would be sort of a flat-looking bell-shaped curve. Right? As this would be my mean, and again, the values would be fairly spread, so it would be flat. It would be a fat-looking curve. If it's a small standard deviation, all of them are fairly tightly packed in the mean. Alright, so I'm drawing out my mean, because it's a little easier when I have. This one, again, they'll come in fairly quick quickly reach the peak and then come out. And so, like I said, it would be a very skinny, thin-looking bell shape. Still bell shape, still symmetrical. Half of the points land above, half of the points land below. But the majority of them are pretty darn close to that average. I would have a small deviation. And we're going to talk more in detail about it. There's actually a special relationship between the standard deviation and the bell-shaped curve, and then the percent of values below it. Now, that very special rule, which we're going to do examples in a little bit, is called the rule of thumb for a normal curve. It's called the 68, 95, 99.7 rule. All right, and this works for any set of data values that are called normal. So if it's normal distribution, this rule of thumb works. And what this means, all right, so it's giving you the percent. 68% of all of the data values, all of the values in our normal set, will land one standard deviation from the mean. So again, if I write my mean as mu, there's my mean, and sigma as my standard deviation, 68% all of the data values will be between the mean plus minus the standard deviation. Right? That's what that means. It means if the mean is 10, the standard deviation is 5. All of the data set, 68% of the data values will land between, add 5, so 15 subtract 5, 5. So between 5 and 15. Alright, the 95 means 95% of all of the data values will land within 2 standard deviations. So that means 95% of all of the values in the set, if it's normal, will be between the mean plus minus 2 times the standard deviation. So 2 standard deviations away. So again, if the mean was 20 and the standard deviation was 2, so what we'd mean is we'd 20 plus or minus 2 times 2. So they'd land within 4 units above or 4 units below. That's what that means. So 2. You would take your standard deviation and multiply by 2. Almost all. Pretty darn close to all. Right? 100% would represent all of the data values. So 99.7, all but 0.3% of the values land within 3 deviations from the mean. So if you take your mean and you would add and subtract 3 times the deviation, so if I did this case here, that would be 20 plus or minus 3 times 2. So almost all, 99.7%, would land within 6 units of 20. So they'd be between 26 and 14. Almost every single data point on our list would land, 99.7% of them will land between 26, if this were an example that we did. So the picture, how that goes along with our bell-shaped curve. So the graphical breakdown, so remember, this is the mean, which is equal to the median, which is equal to the mode. Right? So again, it's the middlemost value, the average value, and the value that occurs the most often. 68% of the data values land within 1 standard deviation. And so that means 1 deviation above and 1 deviation below. So if mu is my mean, sigma is my standard deviation, this value would be whatever my mean was plus 1 standard deviation. This value would be whatever my mean was minus 1 standard deviation. 68% of the group lands there, and because we have symmetry, we can actually break it down by parts. Right? If I took, again, half of the 68% will be above, half of the 68% will be below. And so that's where this 34% comes from. The 34% is the half of the 68 that's above, 1 standard deviation away, so we add the deviation, and half of it's below, so we'd subtract the deviation from whatever my average was. Alright, then the 95. So the 95 would be these points out here. So 95% of the set lands within 2 standard deviations. So I take my mean, and this value would be, I would add 2 deviations to get here, and this would be, I take my mean and I subtract 2 deviations to get there. 95% of them land here, and so I know half of them would be 47%, 47 and a half if I took 95 divided by 2. Right, it would come out to be 47 and a half, right? If you took your 95 divided by 2, it's 47 and a half. So half of it would be 47.5 over here, 47.5 over there. So half of the 95 lands above the mean, half of the 95% lands below the mean, meaning half of it is 2 standard deviations above, half of it is 2 standard deviations below. And so again, we can sort of take that, so that green area comes from the additional getting to the 47.5. So you take 34 minus the 47.5, and that's where that 13.5% comes from, right? That's the total area where 95% of the data lies. All right, so then the last one. Last one is our 99%, almost all, 99.7%. The only thing that's left over would be 0.3% is outside of the 3 standard deviations. All right, so again, putting it in my table, so 97, so if I pick a value, 99.7% of them will land 3 standard deviations away. So this point here would be taking my mean, adding 3 deviations, and then this would be the value where I take my mean and I'd subtract 3 deviations, which means almost all of it, 99.7%, is the majority of the points in our set land within 3 deviations from the mean. So there's just a little bit left outside, all right, 0.3%, and the 0.3% would be split, half of that's above and half of that's below. So that's where this 0.15 comes from. That's the 3.3%, so 0.3% lands outside of 3 standard. So those would be sort of our outliers. It's very rare to land outside 3 standard deviations in a normal curve. Half of that's above, so we take our 0.3% and divide it by 2. That's where the 0.15% is, and half of it's below. All right, so again, that's where the symmetry comes into play. That's what makes it symmetrical, right? If I took that and I divided it over the mean, all of those areas would overlap exactly the same, right? We have the same exact shape above the mean as we do below the mean, the same areas above as we do below, all right? And then they land in the same spots. So if I do sort of a generic example, just to kind of set this up. All right, so again, suppose that my mean is 20 and my standard deviation is 2. All right, so if I draw my bell-shaped curve as symmetrical as I can draw it in freehand, so this would be 20, right? My average value for this set is 20, my mean value for this set is 20, and my middle value, my median, is 20. If I go 1 standard deviation, which means I add 1 a deviation, I subtract 1 deviation, and so if we add 1, that would put us up at 22, we subtract 1, that would put us down at 18. That would be the 68%, right? That would be the 68% that lands there. 1 deviation away. 68%. It's the 34%, 34%. Alright, now if I go 2 deviations, so again, it's the same distance, so I add 2 deviations. 2 deviations would be 2 times the deviation, so I'd be adding 4. I'd add another 2, and I'd subtract another 2. So I'd go up to 24, and I'd go down to 16. Right, that would be 2 deviations away. That would be the 95%, right, if I go 2 deviations away. So this is that 13.5, 13.5. Alright, the last one would go a 3rd deviation away. So now I'm going to add another deviation, and I'm going to subtract another deviation. So I'm going to go another 2 over and another 2 back. So this would put me at 26 and 14. 26 and 14 would represent almost all, right? 99.7% of the data values of this particular set. Almost all of the numbers land between 14 and 26. Alright, so if I pick a number, it should be between 14 and 26. There's the very rare outcome that'll land bigger than 26, and the very rare outcome that'll land less than it. Again, remember, that would be only 0.15%. 0.15% chance to be outside of 26 and 14. To be bigger than 26, there's only a 0.15% there, and to be less than 14, there's only a 0.5% that land there. Alright, and so that's the rule of thumb for normal distributions, the 68, 95, 99.7 rule. And we're just going to practice this. We're going to do examples. So the next set of notes are going to be examples of this, and I'll just do one example at a time.